Good afternoon, Panthers. How are you doing? It is Dr. Augustine. Today we are going to be taking a look at our second of 4 videos on section 17.4 intro. And we're specifically going to look at strong acid and strong base titration. So what that means is we have a strong acid and we react it with a strong base, or vice versa, strong base and react it with a strong acid. If you remember in the last video, I said if you have a strong base reacted with a strong acid, it's basically the same curve, just goes the opposite direction. Okay, so every idea we talk about in this video will be relevant whether you're titrating a strong acid with a strong base or vice versa, strong base with a strong acid. You'll just invert the curve and go this way. Okay, so some major ideas that we need to look at. Last video, we were able to identify which one, kind of what the general shape of a strong acid, strong base curve is. And I'm just going to say strong acid, strong base from here on out, assuming that the ideas are exactly the same in the other case. Remember, you have a curve where you have a really steep part right near the equivalence point, and it's relatively flat on the ends. So it kind of stays relatively flat. You notice the pH change here from 0 to 45 milliliters or something is only like 1 pH unit. And from here, about 55 milliliters out to 80 milliliters, it's not even 1 pH unit. So pH barely changes here, shoots up really fast at the equivalence point, and then flattens off again. That's what the typical curves looks like. Now, as we mentioned in the last video, we can do an experiment to like with a pH meter and a burette, and we can actually take data and measure this curve out. But the point of this video and this section of the book is we can actually calculate a theoretical curve using our knowledge of what pH is and also using our knowledge of how to do calculations of H3O plus concentrations. So just using that knowledge, we can actually map out this entire curve, and I'm calling this the theoretical titration curve. So this video is going to be how to generate a theoretical titration curve. Now look, the most important equation whenever we talk about this is the pH equation. pH equals negative log of H3O plus concentration. And remember these little square brackets, that means molar concentration. So if you have the moles per liter of H3O plus, we can calculate what the pH is. So that's our goal every single time, is to find the molarity of H3O plus in my solution. And I'm going to give you a strategy. Now, as I mentioned in the last video, the first thing you should do on one of these titration problems is look at what are my actual acids and bases, what type are they? So if you've identified you have a strong acid and a strong base, like HCl and sodium hydroxide is kind of the classic example. So let's start with that reaction, because that's the one we're going to do. HCl aqueous plus NaOH aqueous yields. Remember, this is actually a Gen Chem 1 topic. This is an exchange reaction, so we end up forming salt plus water, NaCl aqueous plus H2O liquid. And if you remember back in Gen Chem 1, we've got some spectator ions. The chloride isn't involved in the reaction. The sodium isn't involved in the reaction. The salt is not involved in the reaction. So we can rewrite this as H plus aqueous plus OH minus aqueous yields H2O liquid. That's called the net ionic equation. And then also remember, in this part of the book, we've learned whenever you see H plus, that really means H3O plus. So that means H3O plus aqueous plus OH minus aqueous yields 2 H2Os liquids. And then the other thing we pointed out in the last video is these acid-base reactions, the arrow is always going forward. This is not an equilibrium reaction. It is a very highly favored reaction in the forward direction towards the formation of products. Okay, so here's our guiding reaction then. H3O plus OH minus yields 2 H2Os with the reaction in the forward direction. That's going to be our reaction used for everything. So going back to the pH curve that we looked at in the other video, I pointed out that for the weak acid, strong base case, we could break this pH curve into different regions when we were to calculate the theoretical pHs. You can actually do the same thing here. So I have called these 4 different regions, cleverly enough, region 1, regions 2 and 4, and regions 3. So what are those different regions? So region 1 is right at the beginning. In other words, no NaOH has been added, no titrant has been added to this reaction. We'll call that region 1. So that's right at the beginning of the reaction. Region 2 is going to be this region right after the very beginning and right up to the equivalence point, but not including the equivalence point. That's region 2, and I'm going to call region 4 just past the equivalence point, going on up to wherever. I mean, you just keep adding base and you get this. This is actually a limiting reagent problem. And then region 3 is actually at the equivalence point. So there's 3 distinct regions with 3 distinct ways to solve these problems. Now, so I'm going to label these on the drawing. Region 1, this is actually a chapter 16 problem. You've already done a bunch of these problems. Region 2, this is a limiting reagent and an excess reagent problem. Actually, region 2 and region 4. And then region 3 is at the equivalence point. And this one, you can simplify your life. It's just pH equals a 7 at the equivalence point. By the way, pH equals a 7 only for a strong acid, strong base case, and I'll tell you why in a second. So to make region 2 and region 4 are the hardest ones to deal with. So let me just add one little more piece of information here, and then we're actually going to take a look at some examples of this. So before the equivalence point and after the very initial point, this is going to be excess H3O plus. That's going to be our excess reagent. And then after the equivalence point and all the way out to whenever, this is going to be excess OH minus. All right, so in this region here, all we need to do is calculate how many moles of excess H3O plus there are and divide it by the new volume, because you're going to be adding volume to whatever your starting amount was. That will give us the molarity of H3O plus, and then we use the pH formula. For the region past the equivalence point, we're going to have an excess amount of hydroxide, so then we can calculate the pOH, which, if you recall, is basically the same formula. pOH is equal to negative log of the concentration of OH minus. And then, of course, you remember pH plus pOH is equal to 14. So using these two equations, we can figure out what the pH is of the solution once we get beyond the equivalence point. Okay, welcome back, Panthers. I've cleaned up the mess I made of this titration curve, so it's a little bit clearer to look at. We're going to take a look at region 1 first. This is the easiest problem. If your professor gives you one of these, you're going to say, thank you, Dr. Augustine, because this is not a hard problem at all. This is actually a chapter 16 type problem. So here's an example of what this might look like. It's phrased in terms of a titration, but really think about it. You have not added any base to it. So because you've added 0 of the base, it's basically calculate the pH of a 0.25 molar aqueous solution of HCl, or any other concentration, or any other strong acid or strong base. It's a problem you did in the last chapter. You're given the concentration of a strong acid or a strong base. You haven't titrated it with anything. Find the pH of that strong acid or strong base. Okay? So let's take a look at that problem first. So just so we're clear, because HCl is a monoprotic acid, it's actually easy to not recognize what's going on and possibly make a mistake with this. But if you have something like sulfuric acid, which is another strong acid and is not monoprotic, sulfuric, reminder, H2SO4, there's 2 hydrogen H pluses in every one of these. So here's the reaction, the dissociation reaction. Remember, whenever you see an AQ, that really means it's broken up into its ions. So really in solution, it's H plus aqueous plus Cl minus aqueous. So technically, we really need to write down the concentrations here. So we've got a 0.25 molar HCl solution, which means 0.25 moles HCl for every 1 liter of solution. And it's probably a good idea to do a little calculation to say I got 1 mole H plus for every 1 mole of HCl. And that's going to cancel that. So that's going to give me 0.25 moles H3O, H plus for every 1 liter of solution. In other words, the molarity of this solution is equal to 0.25 molar in H plus. And then also remember, whenever we say H plus, that really means H3O plus. Okay? So because of this reality, if you have a problem like this, it's actually a really easy problem because you already have the concentration of H plus, and we know that pH is equal to negative log of the molar concentration of H3O plus. So this is just negative log of 0.25, which is equal to 0.60. So the pH of this starting solution is less than 1, 0.60. All right, so you recognize this first part of this curve. If you have a problem where you have not started the titration, you're back here at 0, volume equal to 0, it's just like a problem that you would have done in the last chapter. You just take the concentration. Okay, the next thing we're going to tackle is region 2. Remember this region here, up 2, but not including the equivalence point. So right from when you start adding stuff to just below the equivalence point, and then region 4, this region just past the equivalence point. So that's like 0.1 milliliter past the equivalence point. So from when you first start adding titrant all the way up to the equivalence point, and then just beyond the equivalence point. Those are regions 2 and 4. We're going to deal with those cases now, and the example I'm going to give you is actually a problem in region 2. Okay, so that's down here. So the question is, calculate the pH of 50 milliliters of a 0.1 molar HCl solution that has been titrated with 27.50 milliliters of a 0.100 molar sodium hydroxide solution. All right, so take a look at the type of problem it is. You've got an acid with a known concentration and a known volume, and you're titrating it with a base with a known concentration and a known volume. And this is not the equivalence point. So you might be thinking, well, that looks an awful lot like a problem back in Gen Chem 1, except we're not actually at the equivalence point. We are somewhere along this curve here. If we were at the equivalence point, you could do a calculation back from Gen Chem 1 where you could calculate how much volume does it take to get to the equivalence point, but we're not there yet. Okay, so this problem is somewhere in this blue region, this region 2. So here's how we attack this problem. Remember, this is our guiding equation. H3O plus OH minus yields 2 water. That's a neutralization reaction. It's the net ionic equation. We've gotten rid of the spectator ions, gotten rid of the sodium, gotten rid of the chloride. All right, so I'm going to create a mole table. It's going to look a lot like an ice table, but it's not exactly an ice table. So I'm going to say the number of moles initial, right? Not the number of, not the molarity. And I'm going to say the number of moles that change. And then I'm going to say the number of moles final. Why am I doing this? Because I'm trying to figure out what the excess reagent is. One of these is going to end up being a 0. And one of these there's going to be some amount left. The one that's some amount left is the amount of excess reagent that's remaining. The one that's a 0 is the limiting reagent. So we're going to fill in this table with our starting number of moles of H3O plus, our starting number of moles of OH minus, and then whichever one is the smaller one, since they're in a 1-to-1 ratio, it's going to go down by that much, and that'll give us the amount that's final. So what I'm going to do is, a good thing for you to do would be to stop the video and see if you can calculate the initial number of moles of H3O plus and the initial number of moles of OH minus from the information that we have in this problem right here, and see if you can fill out this entire side of the table. In fact, that's the only side of the table we worry about. So try to figure out what should go in this table. There should be 1, 2, 3, 4, 5, 6 numbers that will get filled into this table. We're going to have an initial number of moles of H3O plus, initial number of moles of OH minus, a change, and then a final amount, and that's actually telling us what the excess reagent is. Okay, so I've filled in the first 2 slots here. There's 5 times 10 to the minus 3 moles of H3O plus. That's based on the molarity times the volume. And then we've got 2.75 times 10 to the minus 3 moles of OH minus. That's based on, again, the molarity times the volume. Remember, always molarity times volume is number of moles. So if we look at these 2 numbers, we know these are in a 1-to-1 ratio. So every one of these that goes in, one of these is going to drop down. So since this is a smaller number than this is going to be the limiting reagent. By the way, be careful. This is not molarities. This is not the same as an ice table. This is a number of moles table. So let's subtract off the 2.75. So minus 2.75 times 10 to the minus 3. So we're going to have 0 moles of hydroxide. It's all going to get used up in the reaction. This one's going to be minus 2.75 times 10 to the minus 3. So we are going to be left with 2.25 times 10 to the minus 3 moles H3O plus. Okay, that's the excess reagent. So in region 2 in this curve, we have excess H3O plus concentration. So from just after the beginning to just up to the equivalence point, this is going to be excess H3O plus. Past the equivalence point, this is going to be excess OH minus. So we can now we have the information that we need to figure out what the pH is in this particular point in time. At 27.50 milliliters addition, we can figure out what the pH is. But we're not quite there yet, because if you look at this, pH is negative log of H3O plus concentration. Remember, that's molar concentration. We just found the number of moles. We didn't find the molar concentration. So we need to find the molar concentration of H3O plus, which is that number of moles divided by the volume. Where's the volume coming from? It's the addition of the starting volume of HCl, plus we added to it 27.5 milliliters. So my molarity is actually the new number of moles divided by the new volume. This would be a good time for you to see if you can do that calculation, and then I'll come back in a second with the answer. Okay, so our number of moles is 2.25 times 10 to the minus 3. My volume is now 0.05 plus 0.0275. So my new molarity is 2.9 times 10 to the minus 2 molar, and therefore the pH is going to be equal to negative log of that new molar concentration, 2.90 times 10 to the minus 2, which is equal to 1.53. Okay, so in summary, we have now found the pH of some particular point on here. If you recall, the last one was 0.6, so it's gone up a little bit. It's 1.53. It is a little bit higher than the pH was before, but not an awful lot higher. And using this strategy for regions 2 and 4, we can calculate any point along this curve as long as we know how many excess moles of either the H3O plus is or the OH minus. If we have OH minus, we're not going to find the pH, we're actually going to find the POH. POH will equal to negative log of the OH minus concentration. And again, remember, you have to find the molarity, not just number of moles. So we'll have moles from this mole table, and we're going to have to divide that by whatever that new volume is. So that takes care of regions 2 and 4. Region 3, you don't even need a calculation. You know that the number of moles of H3O plus is equal to the number of moles of OH minus. Therefore, you've completely neutralized your reaction, and hence the pH is equal to 7. You have a pure water solution, and you can actually use the auto-ionization of water equation to figure out what the pH is, but we already know the pH is equal to 7. There are no other ions in solution. It's just H2O, so the pH should be 7 for a strong acid, strong base calculation. Just reiterate one more time. If you have a weak acid or a weak base, you're not going to have a pH of 7 at the equivalence point. But for a strong acid, strong base case, you'll have a pH of 7. Okay, that takes care of video number 2. Strong acids, strong bases, reacting and titrating. There's some example problems. You should be able to do any point along this curve, and any one of those is fair game for a question. And remember, if it's a strong base, strong acid, it's just the exact same curve, just mirror image. It'll start high, the base will have a high pH to start with, and it'll drop down and get flattened out once it gets past the equivalence point.